I'm speaking today to Jonathan Allday and Simon Hans. Jonathan is well known for writing classic texts on quantum theory and general relativity, amongst other books. And Simon is a theoretical physicist who has worked at Swansea University and is now at the University of Liverpool and has over 100 research publications to his name. They now jointly produced a new book entitled An Introduction to Entropy, subtitled The Way of the World. I suppose that could be the way of the universe, really, because it covers probably everything. But Jonathan and Simon, thank you very much for joining me today.
Thank you for the invite.
Can I ask you, just to begin with, why is entropy worth writing a book about?
Well, I think one of the unusual things possibly about this particular book is that both Simon and I were at school together. We were a year apart at school and we went through university together. And Simon has been very helpful to me over the last few years as being kind of my physics conscience in writing other books. I've sent chapters to him to make sure I wasn't getting the maths completely wrong, that sort of thing. And we enjoyed that interaction, and we got to the end of that, and we both, I kind of think independently, decided it would be nice to write a book together. And I don't know which of us suggested it to the other.
Well, the actual order of events was that you asked me to track down various research publications because I benefit from a subscription to a university library. And in particular, you asked me to find the paper by Jacob Bekenstein for the entropy of a black hole. And I sort of thought, like, I had a glance through it. It's a fairly short paper, and I read it before sending it on, and I thought, wow, that's such an interesting way of approaching this topic. I never knew that. And then a couple of weeks later, and probably a couple of glasses of red wine later, I actually had the idea I proposed to you that we think about your next book involving me as well and involving entropy as well. And you replied saying I was having the same thoughts. So
okay, cool. But I think the point is that we'd both gone through an unusually, for co-authors, an unusually parallel education in physics, certainly up to graduate level. And we both came out of it, and looking back 30 odd years later, Simon, professional career in physics, me, a professional career in teaching, which admittedly didn't often involve entropy in the classroom. It regrettably isn't part of standard syllabuses. But anyway, we really didn't know what we were talking about. We didn't know what entropy was. Was it just a common word that was used in multiple different ways? Was it an underlying concept that existed? And we kind of felt there wasn't a book out there that approached it from that point of view. There are many books about individual aspects of entropy, and you kind of move from one lecture hall to another, and the word is mentioned. But is there this common thread underneath them all? Or is it like a collective noun, like games, that actually means a whole variety of different things to different people? Simon, would you agree that was kind of the motivation behind it?
In retrospect, yes, I think it describes where we got to quite well. I just thought Bekenstein's paper was really cool, and not something I'd ever looked at before. But I've had a long-standing interest in thinking about entropy and talking about it from I would say an amateur perspective. And one of the things I wanted to bring into the book was this kind of cultural perspective. How does entropy kind of transmit itself? How is it thought of outside the classroom and outside the laboratory? And there is this sort of very famous quote by C.P. Snow, which we set out and then riff on it throughout the rest of the book. That he delivered this lecture, The Two Cultures, where he said that famously, literary intellectuals were very scornful of scientists because they hadn't read many books, and they didn't seem to be able to hold their own in conversation. And his response was to ask them what they knew about the second law of thermodynamics. And he said their response was cold and hostile. And he said what they didn't know was I was asking them the equivalent of, have you read a work by Shakespeare? So C.P. Snow, who I've got mixed feelings about, but clearly thought that entropy was very important in our world and should be more widely appreciated. And you know, I hope we've sort of managed to make the case on Snow's behalf.
Well, one of the things which came out very forcefully to me when I was looking through your book, I can't say I've read it in detail because it's quite a textbook, really, isn't it? It's got probably 1,000 equations in it. It's not designed, I think, for the layman to read, but someone who wants to really understand and grapple with the issue properly. But one thing which came out to me from the book was that there's not just kind of one entropy, is there? There's a thermodynamic entropy, there's a statistical entropy, there's maybe a chemical entropy, a quantum entropy, an informational entropy, and maybe even a black hole entropy. So,
I mean, when we started, I just assumed that it was all the same thing, and it was Jonathan who insisted on giving them all different labels.
well, my question is,
distinguishing between them, and I think I learned a lot from that. His caution.
Yeah, but the question which comes out from that then is, if all of these different fields use the term entropy, are they using the same term, or have they got different meanings for it depending on which discipline you're from or which defined it? Is there an entropy behind all of this, or are they 6 or 7 different things entirely which just happen to be called the same thing?
I think it's split off, actually, in some ways. I mean, there was the moment when Shannon was working in information theory and had this particular quantity that he wanted to name. And I think Simon will correct me, or you will, von Neumann suggested, well, there was this idea that it should be called entropy. And he said, well, you may as well call it entropy because no one knows what that means anyway. And I think since then, things like there have been various branches of entropy, particularly quantum entropy or that sort of thing, which was spun off that information theory idea. And so there's a commonality there, but I'm not sure there's a commonality between that and the entropy that people would be familiar with from working with gases and that sort of thing. I think there's been a split off there at that particular point. Although I think you can draw some threads between those two splits. It's not quite so obvious where those threads are, but I think we've managed to unearth them.
Let me tell you from another direction. When we started off, we followed the path of which you would follow as a physics undergraduate. Jonathan's already said that that's where we both come from. So we start off with a lot of careful discussion about gases and heat and work, and only very gradually get round to introducing entropy through some quite subtle, difficult arguments, which all beginning physics students are kind of dragged through when they're usually fairly early on in their studies. And we were showing those early chapters to a group of friendly readers based in the United States who Jonathan knows, and they're familiar with Jonathan's other books. And they said, why are you telling us all this stuff about gases? Well, let's hear about entropy. These guys had a background in electronic engineering, and their approach to entropy was completely different and much more influenced by the ideas of Shannon and information theory and how to effectively and accurately communicate signals. So they were using the same word, and they didn't know and didn't care about gases and pistons and cylinders and Carnot cycles and all those things. So that was a complete eye-opener to me, and it just illustrates the points that we've been making.
Yeah, I think the point about, I mean, Simon wrote that section, that very careful development of what you might call the undergraduate approach to entropy or the classical approach to entropy, is you end up with this notion that entropy is something real. I mean, it's there with heat and work and all those other
no, let me correct you, Jonathan. It's better than heat and work. Heat and work It's a technical point, but
Yes, you're right. Yeah.
we start off when we learn thermodynamics talking about heat and work because everybody knows what they are. Heat is what you get from a Bunsen burner or a coal fire. Work is what you do when you lift a weight. These are terms that we've all developed to find our way around the world. And what careful study of classical thermodynamics tells you is that they're not really fully developed, independent physical concepts because they depend on history. There are other quantities, and energy is one of them, and entropy, it turns out, is one of them, which are state functions. They just exist absolutely as a property of a system which you can determine or calculate without knowing how it got to be there, without having any knowledge of its preparation.
That's very fair. But the only point I would add to that is that you end up with that, but you still really don't know what entropy is. You know, it's a number that means something. You know, it's a number that you can use to calculate, and you know it's a very helpful aspect. And as Simon says, it's real in the sense that it's not functionally dependent on the history. But what is it? And that's kind of where you get to at the end of classical thermodynamics. And, you know, as we all know, classical thermodynamics is in a sense underpinned by statistical thermodynamics. And you have got an idea of what you mean by pressure as a picture of molecules banging against walls, and the volume is the space that the molecules occupy. So there is a kind of micro explanation for a lot of the aspects of what you see at the macro scale in this classical thermodynamics. So the next step is to say, okay, then, well, is there a micro thing underneath it all which explains what entropy is? And that's the kind of next layer down. So
can I come to that?
The opening part kind of establishes entropy as a thing. You know, it's a real thing, it's a really important thing, but we don't know what it is. Okay, so how can we now pursue what it is?
Yes, and you need the atomic theory of particles to start to dig down a bit deeper into that. I mean, you mentioned it comes from the ideas of heat and temperature. And it's interesting, the difference between heat and temperature when you look at atomic theory is that you've got the jiggling of atoms moving around like that. They've all got a kinetic energy. And if you have the total kinetic energy, in some way you could measure the total kinetic of a system, then you have a quantity of heat. If you take the average of the method of the kinetic energy, then you have essentially a temperature, which is why, for example, you can have a high temperature for my cup of coffee here, but it has less heat in it than, say, an iceberg does, because the iceberg has far more molecules moving around, far more kinetic energy involved in that. Now, is entropy something which can be distilled back in the same way that heat and temperature can be defined? Can it be defined in those kind of terms? And if so, what's the definition?
Let me try. The answer is yes, and in fact, I would take issue with you're ascribing a quantity of heat to an iceberg or to a cup of tea.
That's my
rule
of thumb.
Let's go back. Let's go back because I thought about this quite a bit, and let's start off with the atomic picture. We've known for over 100 years that everything's made of atoms. If we're talking about a gas, that's atoms flying all over the place, bouncing off each other, bouncing off the walls of the room like a hail of bullets. If we're talking about a solid, a crystalline solid, then you can think of atoms as being like an array of marbles all sitting on top of each other in some ordered way. So ultimately, our fundamental description of stuff must be in terms of the atoms, where they are and how fast they're moving. And we can ascribe things like kinetic energy to the atoms and probably potential energy as well if we're talking about an atom in a solid. If we wanted a complete picture of what was going to happen and what was going to happen next, which is an important part of physical science, we'd have to keep track of an enormous number of variables. and everybody knows how to quantify this. It's always Avogadro's number 10 to the 23. You know, if you we don't have the means to do measurements of that number of variables. We certainly don't have the means to do calculations or to compute with them. So although we've got this kind of fundamental picture, it's of limited practical view, use. Let's focus on the gas, because everybody does in this subject. We know that there's a much simpler description of gases, which is also enormously powerful and useful. And this focuses on the bulk properties of the gas, such as its volume, such as its density, such as the pressure it exerts on the walls of the container, such as its temperature. These are all things that we've got much clearer idea of what innately of what they mean. They're things we've been working with since the Industrial Revolution. And you can describe the gas with a much smaller number of variables, maybe a handful. So this is, in modern parlance, we would call this description of gases an effective theory, but an extremely useful one which throws out all the detail, just focuses on stuff which helps us understand gases and helps us do things. In effect, we've thrown away a lot of information about the gas to concentrate on this effective description in terms of pressure and volume and temperature. Entropy is an objective quantification of how much information we've thrown away. And in order to understand that, you can take it on trust, but you can do this with anything which can be counted. We can count atoms. And if we can count atoms, we can count how many are on this side of the box and how many are on this side of the box. And from that, we can construct all sorts of different measures of how much information we need to describe the gas. And entropy is a particularly simple and neat form which helps us do that. At that level, it's kind of just a mathematical toy. The astonishing thing is that in the limit where we are talking about huge numbers of atoms, Avogadro's number, and in the limit where things are stable, things are in thermodynamic equilibrium, then the definition of entropy in terms of information loss coincides with the definition of entropy in terms of heat and temperature. These classical concepts which are much older. And that actually is a miraculous thing. The fact that they coincide in that limit. And this insight was first down to Ludwig Boltzmann, and it's encapsulated in a very famous equation, which Jonathan is wearing on his t-shirt. I hope you're not going to get closer to the camera, Jonathan. Please don't. But...
Right. So does that give us a definition of entropy?
It aligns two different definitions. That sounds like rather mealy-mouthed of me, but there is a perfectly adequate classical definition of entropy, as Simon says, from the function of state, and there is a perfectly good definition of something called entropy, based on information, or rather the lack of information you may have in a similar circumstance. What Simon is saying is, in the thermodynamic limit, those two happen to coincide.
Yeah, so let me be the lawyer with all the caveats. In the macro world, the classical definition of entropy, that really is only solid in the thermodynamic limit, the limit where you have a lot of particles, and also in the limit where you can only really be certain of calculating the entropy or measuring the entropy properly in the limit where you're working very close to thermal equilibrium. So in other words, there mustn't be any drafts, there mustn't be any sudden changes of pressure or volume. Everything must happen very slowly and gradually. So there's a limiting process in which you can be certain you know what the entropy is. In the micro description, the statistical description, actually calculating this information loss depends on a process called coarse graining. There are different ways to do the calculation, and they will all get slightly different answers. But again, you can show that in the limit of a very large number of particles, they'll essentially all agree that the differences between those answers will become unimportant. So yes, there is an entropy, but there is a kind of an understood definition of entropy, but we approach it. We kind of approach it. We can't just I think naively hope to determine the entropy of something.
But what I'm trying to pin down here is what exactly is entropy? If you look at it from a thermodynamic point of view or a statistical point of view, you could say it's the amount of disorder in the system. You've mentioned that from an information point of view, it's the amount of information that you throw away in a system. But what is it? I mean, are they two the same or are they different? And what is entropy at the heart of the matter?
Let me try this. We've both got coffee mugs. Now, this coffee mug and the liquid it contains is in a certain state. It has a certain volume, temperature, there's a pressure exerted inside, everything like that. But as Simon's been saying, the actual distributions of the molecules and the atoms within this, the exact distribution that's happening right now at this moment is its micro state. So there's a macro state, which is what we can touch and feel and measure. And there's a micro state, which actually is the way in which the atoms are arranged right now. Now, there are multiple different micro states which are compatible with the macro state. In other words, if I move an atom from here to here, it doesn't make a blind bit of difference, but that is a different micro state. So the entropy is a count of the number of microstates which are equivalent to the particular macro state that you find yourself in. That's what I would say. And as Simon is saying, the information loss is that we don't know which microstate it actually happens to be in, and we can't know because we can't measure to that degree of precision. If we want to predict the future, we would have to know the exact microstate, and each possible microstate would wander in a particular direction. But we can't do that because we don't know what the microstate is. But after time, the possibilities for the macrostate get wider and wider and wider because each of these microstates is leading off in a slightly different direction. And so therefore the count of possible microstates compatible with how we find out this coffee mug evolves in time is getting bigger and bigger and bigger. And that's why the entropy increases.
So is entropy just a statistical measure, nothing else?
It's an informational measure.
I think I agree with Jonathan. It's really telling us about the information we have.
And how does the information connect to the statistical picture then? I mean, you have a very interesting chapter in here about information. It's a very nice chapter because it's quite illustrative. And for example, you even talk about not just Shannon, but you look at, say, the works of Shakespeare, and you say that Shakespeare's got an entropy of, I'm looking up here, 4.098, whereas Moby Dick has got an entropy of 4.124.
Good, yeah. So
what
now,
does that mean?
What does that mean? Yeah. So there we're using the word entropy in the Shannon sense.
Yeah.
And the math. It's the reason he saw fit to call it entropy, I think, is basically the mathematical equation that he used is identical to the mathematical equation for entropy written down by Gibbs.
Yeah.
It's the same form. He's actually using the term in a. It's funny when we've been talking about entropy up to now in terms of information that we've lost when we focus on the macro state. Shannon was using the same word in the opposite direction. He was actually using it in an attempt to quantify the information. In Shannon's world, all the different microstates are different messages, and they are distinct because they all carry distinct meaning. And Shannon's trying to quantify the amount of meaning that can be squeezed through a communication channel, such as a telegraph wire. in a given time. There is, so on the face of it, they're not quite the same thing. But then when there are people who haven't been content with that and have sort of driven things further and said there are limits in which actually, yes, information in the Shannon sense is related to thermodynamic entropy. Later in the book, we cover the work of, we cover arguments by, well, first of all, Shannon himself, when he talks about how a gene reproduces itself, or how a strand of DNA is reproduced. That's sort of information transfer, which requires on a certain amount of entropy being spent. We also talk about the work of Freeman Dyson, or his argument that human civilization could continue indefinitely, and he quantifies this both by the thermodynamic constraints of living in a world which is slowly getting colder and colder, but also in the informational constraints, the information processing that goes on in a human mind, or a human-like mind, to enable them to compose sonnets or to prove theorems.
Can I go back to just something you just said?
Please do, yeah.
That the information definition by Shannon is not quite the same as the one from the thermodynamics, but they both use the same kind of formula. So
yes,
are you basically saying that really entropy in one field is just different from the other only because it applies to different objects, but it behaves exactly the same because the formula is the same? In other words, one applies to bits.
Okay, yeah, that's a fair point.
And the other one applies to atoms.
I think sometimes the word entropy has been co-opted into different fields because this formula is so similar. And it's not clear that conceptually it's the same thing just because the formulas echo one another.
Yes, we want in particular to call out entanglement entropy, which is an aspect of von Neumann entropy. That uses that the formula for entanglement entropy is recognizable, and it's a quantity which is certainly can be calculated, and it's a useful quantity, but it doesn't obey the second law, and it's not extensive. In other words, it doesn't depend on the size of the system.
Can I come back to
if I could just come back to information for a second. Sorry to interrupt.
No, go ahead.
But I think there's an important point to make here, which is we're aligning entropy with information. The problem is information itself is almost as ill-defined a concept as entropy is. So we're kind of nailing two slightly vague concepts together. And certainly when, in the technical sense, when Shannon was talking about information, it's not really information as the layperson might understand it. Because, clearly a sentence that makes sense conveys information to people. It informs them about the state of the world or the state of a person. But that's not what information was in Shannon's sense. It was a count of, really, if you imagine a sentence comprised of a certain number of characters, it's how structured is that sentence, rather than is it just a random collection of characters.
Actually, Shannon can only calculate the entropy of Shakespeare or of Moby Dick by having previously studied a huge amount of blocks of meaningful English text. In other words, the entropy derives from a frequency analysis of the rate at which letters or groups of letters or words apply. So the entropy that Shannon's talking about doesn't exist in a vacuum. It's actually derived or calculated based on close observation of existing text.
Okay, but what does it actually mean?
Then?
Well, what does it actually mean to say that you've calculated that Shakespeare's got 4.098 entropy and Moby Dick is 4.124 entropy? Does that mean that one book is more randomly disorganized than another? What does it mean? What does it actually come down to?
I think that's it. It's a measure of how much structure there is present in the block of text compared to a randomly distributed set of letters, a set of characters of equal length.
So Shakespeare is slightly more organized than Herman Melville.
I don't think, well, okay, I don't think any of those, I don't think any of those differences, the numerical differences between the different works of literature, are probably that significant. One of the things I was trying to illustrate was actually that they were all remarkably similar, except that I thought the interesting case was the two versions of Les Miserables, the original French and the English an English translation. And I think there was a difference in entropy there, which possibly reflects the structural differences between French and English language. More likely just reflecting the differences in letter frequencies in the two languages.
The word meaning has come up a couple of times here, and I think it's important to emphasize that, Shannon's definition of information does not have anything to do with meaning as such. We're not trying to say that one block of text is more meaningful from another. That's not part of it. And yet, if people coming at this from the outside are thinking about information, then they're probably thinking about information and meaning as if not quite synonymous, very close to synonymous. I think the closest we can get there is how structured is it? How much patterning is there in the block of text compared to a randomly distributed set of characters? And that has some analogous relationship to entropy, as we're talking about in the thermodynamic sense, because again, coming back to the number of microstates that are compatible with a particular macrostate. Remember, microstate being how the atoms are actually distributed, macrostate being what we measure, what we can conveniently measure about the system. Then not all of the microstates are equally likely. Some are more likely than others. So there is a structure as such in the pattern of possible microstates. And so entropy reflects in that structure as well.
So from a literary point of view, then, what you're saying is if you're going to use these measures in any way, or if they mean anything at all, they're nothing to do with semantics. It's all to do with syntax.
Correct.
It's a syntactical measure, essentially.
I think that's right. I mean, Shannon was, he didn't do this as a parlor game. He was trying to solve the problem of how do you send messages quickly and accurately. And he was working in wartime. he was really trying to help. And I think we should always stress the practical applications of these mysterious ideas.
Okay.
So one of the chapters, in fact, the closing chapter of the book is actually a conversation between Simon and I, where the word pragmatist comes up, and it's almost, like a term of abuse that I hurl at Simon for being a pragmatic approach to things. One of the things that readers might spot is that my approach to this was far more to do with what does entropy mean from a philosophical point of view. Simon's approach is more pragmatic in the sense that what can you do with it? Both are equally valid, and we hope that they make a nice contrast in the book, but there is that distinct approach to the two.
Okay. Look, can I move us on just a little bit to ask you this question, and because this adds an extra layer or maybe more depth to it. And that is, what does quantum theory, because you have a chapter on this, what does that add to our understanding of entropy?
This is a fascinating question. I'm glad you raised it, because it was in the writing of the book, it kind of almost governed one of the questions we wanted to understand was, is quantum theory essential to have an idea of entropy and even to have a second law of thermodynamics? In one sense, in a trivial sense, yes, it is essential, because we need quantum theory to make atoms stable. Otherwise, they wouldn't be stable entities. And since entropy is a theory which rests on counting atomic states or equivalent things, we need quantum theory. But actually, a lot of the arguments are classical and can remain classical. And the division of labor between Jonathan and myself, I just gave him all the quantum stuff because he likes that. Again, I was more interested in the counting and the calculating. And we got almost all the way through the book, I think, in this happy state, the one time I think I found you really need, it was really necessary to introduce some appreciation of a quantum picture, was the black hole entropy, which is the kind of the last meaty chapter of the book. Let's go back. The black hole in classical general relativity is a very simple object. It can be described by 5 numbers: its mass, how fast it's spinning, and if it's got an electric charge. We know that, well, we believe that if black holes exist, they do exist, but that lots of different things have fallen into them over the period leading to their formation. So all of the information about those things, what fell in, how fast it was going, all that kind of stuff, all that's been lost. It's now hidden from us. So this is clearly the way Bekenstein was thinking. There must be some kind of entropic account of this, because there's information being lost. And his route to the result for the entropy of a black hole was to just assume that when you throw a particle into a black hole, a single particle, could be an electron, could be something very simple, that's like losing a bit of information. So we can quantify that in terms of entropy. And it's the property of the aspect of the black hole which directly relates to this is the surface area of the horizon. It turns out there are mathematical theorems you can prove that no matter what you throw into a black hole, that area can never decrease. And Bekenstein was able to derive a formula which looked like the first law of thermodynamics, but where the role of entropy was taken by the surface area of the horizon. However, in order to make that work, the particle he threw in his thought experiment couldn't be a classical particle. It couldn't be point-like. It actually had to have a physical extent in order for the entropy to be non-vanishing. And the picture of the world which naturally gives us particles which are not points, but which are spread out a little bit, which are fuzzy, is a quantum picture. And the associated size of the particle is something called its Compton wavelength. So that was Bekenstein's route to writing down a formula for the entropy of a black hole in terms of its surface area. Actually, the answer he got is not the currently accepted answer. He was off by a factor of 10 or so, but the route he took, which kind of married classical general relativity, it married quantum theory and all that stuff about Compton radii, and information theory, actually led us to the modern picture, and was very quickly joined by a more rigorous calculation by Stephen Hawking.
So is quantum entropy exactly the same as classical entropy, or is there a difference?
Well, this is partly why we wanted to write the section about quantum theory. I'm going to answer your question, but partly about why we wanted to write it, to find out if that was the case. But just slightly spin back to what your earlier question was: is it necessary? I mean, part of the reason for writing the section, the quantum section, was to find out whether the quantum entropy was compatible. But the other reason was that in the end, all our physical theories at the microstate rely on quantum theory, so you have to explore what's going on there. But just to emphasize one point, Simon mentioned earlier on that if you're going to establish how much information you've lost by disregarding the exact microstate of the system, you come back to this notion that entropy is the amount of information, not necessarily the amount of information you've lost, but maybe the amount of information that you don't have. The amount of information that lies outside of your control. So if I try to specify, if I build a coffee mug, I can't specify the exact microstate that I'm going to produce by building that coffee mug. If I do an experiment on a gas, I can prepare the gas in a particular microstate, but I can't specify the microstate that it has. So to that extent, the entropy measures my lack of control over the microstate, or equivalently, the lack of information I have, my inability to pin down the microstate. But as Simon said, you can't do that unless you can actually do some counting. And generally, the way in which you have to do some counting is this notion of coarse graining. And just to make that slightly more accessible, if I might, for a second, if you've got a whole spread of possibilities with very, very fine subdivisions between them, you almost can't count them. What you've got to do is divide them into blocks, and divide them into blocks and then count the blocks. And what you're actually saying is, okay, there may be 10 of them in this block, but they're all pretty much equivalent. So I can call that 1 and this 2 and that 3. Now, quantum mechanics kind of provides a natural way of doing that, either because you're specifying your microstates in terms of energy levels. That would be one way of doing it. So you've got different energy levels. If it's a particular system, simple system, you could just count the number of different energy levels that are occupied. Or because the uncertainty principle provides a kind of natural blocking in what's called phase space. The idea of phase space being you can specify a particle's, if you can specify its position and momentum, you can specify a point in this thing called phase space, which is just a chart of its position and momentum. Now, it could be almost anywhere, it could be exactly anywhere, but in quantum theory, with the uncertainty principle, you've got this sort of natural size of block, which is proportional to Planck's constant, or indeed, as Simon was saying, with the Compton wavelength. So in that sense, I think quantum theory is necessary in that it provides a natural way of us counting the information that we've lost. One of the big things for me about writing this book was this realization that entropy is more to do with our lack of control over our experimentation. That you cannot pin down the exact microstate, and so therefore you've ceded some control over the way in which the system is going to evolve, and that control is only going to get worse as time develops. And
can you tie this in for us with the idea of the quantum states, pure and mixed states? Does entropy have a difference here? I mean, you talk about von Neumann's approach to entropy, and his nature that I think pure states, you say, have zero entropy.
In the von, well,
how does that tie in with what you've just said?
Well, it in a sense, it undermines, as Simon was saying, this idea of this von Neumann calculation of entropy is actually related to the thermodynamic entropy. What we mean by a pure state is a situation where we know exactly what state the system is in. We know it's in this particular quantum state. If we know it's in that particular quantum state, we say it's a pure state. If, as a result of our preparing some system to do an experiment, and we can never prepare a system exactly the way we want it to, practical limitations. If as a result of preparing the system, we know, our technician comes to us and says, I've got you a system to experiment on here. I've prepared it as best as we can. There's a 20% chance it's in this state, a 30% chance it's in that state, or whatever chance it's in that state. Well, from my perspective, we call that a mixed state. I don't know what it's in. It's a mixture of these different states. It knows what state it's in. There is a state that it is actually in, but I am ignorant because of my lack of ability to prepare it. I am ignorant of which of it is in. I lack information. Therefore, there is an entropy.
The way I understand this. Thank you, Sir Humphrey Davy, by the way, for telling us about your technician. And we're used to, when we talk about quantum theory and quantum mechanics, we're used to the idea that there are limits to our knowledge about a system, quantum uncertainty. We cannot know both the position and the momentum of a particle, and this is a fundamental limit on what can be known. The information loss that's described when we use the term entropy is not of the same nature. It's it's instrumental. It just is resulting from our inability to either measure that many particles that accurately or to calculate with that many particles.
Oh,
And
sorry, can I just ask a clarifying
Yes, go ahead.
question here, which may go to the heart of the matter, I don't know. Is entropy then an objective thing or a subjective thing?
I think it's subjective.
I think
I need to say that by subjective, I do not mean that it's completely in our heads. I mean, it is a measure of our lack of ability to control nature.
Yeah, I think I agree. And I think what it means is that when we think about physics and physical systems, it is legal to imagine that you could keep track of all the particles, all the atoms' motion. You can actually work in a theoretical framework where you can imagine it could be done, whereas you clearly can't work in a theoretical framework where it's possible to know both the momentum and the position of a particle beyond the constraints of the uncertainty principle. That's just not a way you should proceed. So I think entropy is subjective. But again, I come back to it. The miracle is that although it's subjective, by the time you get to big enough systems, no matter what way you're using to calculate the entropy or to measure it, you're always getting the same answer. And that in a sense is an important statement about the world.
That was the eye-opening moment for me, actually, that when the measure of entropy for a pure state is 0. So therefore, what that's telling you is whatever the entropy is, it has got nothing to do with the information that is in the state. It is to do with our knowledge of what the state is that is the measure of the entropy. The pure state, and remember the definition of a pure state being a situation where we know with 100% certainty what quantum state it's in. If that has 0 entropy, that means it's all to do with our ignorance about the state. As distinct from a classical state, if you know the classical state, then you know everything. If you know the quantum state, then there is mystery veiled in that. As Simon has already said, the nature of a quantum state is you can't know the position and the momentum at the same time. And if you manipulate that quantum state, you may well reveal more about position at the cost of fuzzying up the momentum. That's inherent in the state. And that lack of information, you could use the word information there, does not reflect in an entropy measurement. Does not reflect in an entropy measure. So therefore, when you see that what does reflect in an entropy measure is we don't happen to know which quantum state it's in, then it tells us that there is a strong subjective component. Although I'm a bit wary of using the term subjective because it makes it sound a little bit like we've made it up. I think it's all down to our lack of ability to control the situation. And we have to, if you're going to do rigorous experimental science and theoretical science along with it, because the two have to align in the end, then you have to account for your lack of ability to control. And in the end,
now, is this the same subjectivity that would arise from, say, the Copenhagen interpretation that we don't know one thing or another within quantum mechanics, position or momentum, and because we can't prepare things properly, we cannot get that information. But it's deeper than that, because the Copenhagen interpretation says that there is no knowledge of it.
Because there is no physics that determines it.
There is no physics. But alternatively, if you take the Bohmian view, the causal interpretation, or the ontological interpretations it's sometimes called, it says that, the electron does have a specific position and momentum, and that the variation of that is to do with initial conditions. So are we saying essentially that you can view entropy as a subjective epistemological approach, or in the same way that you can view quantum mechanics as an ontological approach, that you have different possible interpretations available, or is that ruled out? Is it purely a subjective element?
I think I've come to the conclusion through writing this that it is subjective in that narrow sense that we mean subjective. in that it is a measure of our lack of ability to control what's happening at the detailed level. And so therefore it aligns more with the Bohmian approach, where the probabilities that are involved are all to do with our ignorance of the exact initial conditions.
Okay.
That would be that's my understanding. You know, it's a very easy. I don't mean to demean it by that, but it's a very easy analogy to say that entropy measures the disorder in the universe. If you examine that in detail, what does one mean by that? How does one you talk about the pack of cards that's either shuffled or it isn't. That's easy to see what you mean in that context, but in other contexts, that doesn't actually not clear what you mean by disorder in that context.
It's like the difficulty with randomness as to defining what that actually means. Yeah.
Right. Whereas if you come back to an idea that it's a measure of our lack of ability to control the initial conditions and therefore the consequences of that as our system evolves, which you could frame in an informational term, as Simon says, you've thrown out a lot of information by taking the macroscopic approach. And the informational sense, again, in that restricted term, not related to meaning, but simply the deviation from randomness. I think that's a much more intuitive idea in many ways, and a one that makes sense to me.
Can I put it this way to you and see if you agree with me? Let's take the pack of cards analogy again, and you randomly shuffle it for however long, and then when you lay out all the cards, you actually find that they're all in order. You know, king, queen, right down to ace, all in suits, and it just happened to turn out. That is a random occurrence. It's been randomly arrived at.
Yeah.
And it's effectively a random state because of that process. But the fact is, we give it a particular meaning. We give that particular state a particular meaning because we see order within it. But that's a subjective projection of ours, is it not, onto the state? And is that what we're talking about when we talk about entropy?
Not quite. If we knew, I mean, I think to make the analogy tighter, we'd have to imagine the shuffling was going on in an opaque ball or something. So you
no, stop.
It started off in. Let me
we actually discussed this.
Disagree with me. Let me finish the point. The point I was going to make was this, and then by all means disagree with me. If you knew what the collection of cards, how it was set up originally, and then you knew all the details of the shuffling process, you could predict exactly what state of cards you'd have at the end of it. And that would mean there was no entropy. And there is an argument which can be done at the classical level, is if you know the exact microstate and you know all the physics involved, you can calculate as far off into the future as you want what the exact microstate is going to be, in which case there is no entropy. The entropy is all to do with our ignorance of how the system is evolving in detail. Again, I come back to because of our inability to control exactly the state it was in. So all I was going to say, and by all means disagree with me, Simon, is if the entropy is all to do with our lack of understanding of what state the cards were in initially and our lack of ability to track exactly what's going on in the shuffling process. Otherwise, we could predict exactly.
I do agree with what you said. I do agree. I just wanted to point out that there is a physics textbook version of this pack of cards example that you've set out, which is called the Joule expansion. So you have a cylinder divided into two, and a gas is confined on one side of that cylinder. So all of the molecules are on the left, say, and then you withdraw the partition, and the molecules all spread out evenly throughout the gas. And this is actually a kind of a classic. It's not just a thought experiment; it's an actual experiment. Now, the standard analysis says that all of the configurations, the subsequent configurations of the gas, after you've withdrawn the partition, are equally probable, including one where everything is still on the left, including the other where everything is actually moved over to the right. They're equally probable, but they are such a vanishingly small representation of all the possibilities that for all practical purposes, you'd have to go through many, many universe lifetimes before this would ever crop up in practice. And a very influential textbook, which we both suffered at university, said that actually the entropy increase in this case, the active was just determined by removing the partition. And I don't actually know a single working physicist who thinks that way. Most physicists, most of the pragmatists who I knock around with, think that the state of the gas where it's evenly spread throughout the cylinder is kind of more likely than the gas where it's all confined one way or the other.
Which textbook are you talking about, Simon? Name it. Which textbook are you talking about?
There's
Not is it?
No, there's a very influential textbook by Brian Pippard, who was head of the Cavendish Laboratory when we were both undergraduates. And I think he took an almost willful approach to the subject. He wanted to get as far as he could in thermodynamics without invoking statistical ideas or quantum ideas. And his book, I don't know, in retrospect, I think his book skewed quite a lot of the teaching of thermodynamics in Cambridge at that time.
We're running out of time as we're rapidly approaching the end of the hour, and I've just really got one last question to ask, and that is, where does all this lead us? I mean, entropy is famously this idea of everything being dispersed out as the two cylinders, as you said. The fact that everything will now end up with equilibrium, and as you quite interestingly quote in the book somewhere, equilibrium is a place where nothing ever happens. What is the future, the long distance future maybe, for the way the universe is going then?
Well, the classic answer is heat death. The universe will become more spread out, colder. Temperature differences between different parts of the universe will become smaller, and it will become harder to make a living. And we basically things happening leads to entropy increasing. So the bleak vision of the future is that it's going to be cold and chilly, and things will slow down quite a lot.
Simon says at the end of the book, one thing about entropy is it's only going to get bigger. And he means that both in topic terms, but also in universal terms. Yeah, the state of thermodynamic equilibrium is where nothing much happens. But I think Freeman Dyson made an interesting point. If nothing much is happening, it's very difficult to be killed in that sort of context. So he actually suggested that life might thrive in this heat death, albeit life at a very different type, and
life but not as we know it. Captain Kirk,
I think to be fair, we didn't want to get too sucked in to what's going to happen down the line, because it's not fully, cosmology, modern cosmology is a very active and rapidly changing field, and things haven't really settled down to the extent that I think we can be certain. But one interesting comment is, if we go back to the idea that entropy is a thing, then actually most of the entropy in the universe is the overwhelming fraction of entropy in the universe is residing in the supermassive black holes in the heart, which seem to exist in the heart of just about every galaxy. That's actually where all the entropy is.
But as you said, the radius of the black hole is always expanding. And presumably will eventually expand to encompass everything.
Who knows? Because we're getting further away from the black holes at the same time.
All right. Jonathan and Simon, thank you ever so much for your time today and for discussing what is quite a complex issue. More, I'm not sure I fully still understand entropy as such, but certainly I would recommend this book here, Introduction to Entropy, The Way of the World. It's by CRC Press, Taylor and Francis Group. I don't think it's cheap, because most of these textbook kind of books are not that cheap, but nevertheless it's well worth getting hold of. And certainly it looks at all of the facets of entropy and does an excellent job of bringing them together. And I like the discussion at the end where clearly you're still ironing out some of the thoughts. But thank you both very much indeed for your time.
Thank you.
Thank you.